All right, for this lesson, you'll need the periodic table and you'll need the bonding unit out for you. So let's take a look here. The bonding unit, it does go back to bonding from what would be the naming section. It's quite a big unit. So what you need to know is you got to know your valence electrons. And in an ionic bond, remember, let's say we have sodium. If we look at sodium, it has one valence electron. So the electron dot figure for sodium, I'm just going to, instead of using a dot, I'm going to use an X so that we can keep track of that sodium electron. And we're going to use chlorine. Chlorine is in group 7A, so it has 7 valence electrons. We're going to use the dots for that. 1, 2, 3, 4, 5, 6, 7. I'm going to put it up there. We know that it just has to have those 7 valence electrons around it. And my ink wasn't dry, but that's no big deal. So what's going to happen is, if we recall, the electronegativity of chlorine is quite high at 3.0. And the electronegativity of sodium is low, but more importantly, the ionization energy for sodium for 1 electron is quite low. So the electronegativity of chlorine here is going to come in and attract that electron from the sodium. And that's going to cause chlorine to have 1, 2, 3, 4, 5, 6, 7, and 8. And since it's gained 1 electron, it's got a -1 charge. That sodium is then going to have a positive charge. Now that plus and that negative are going to attract each other through electrostatic forces, and that's going to basically make this repeating pattern of an ionic compound. We call that a crystal lattice structure. So basically this would repeat over and over again, and you would see many sodium ions attracted to many chloride ions. That's ionic bonding. Now, the electrostatic force is quite strong. So what that means is you're going to have, with the positive ion, known as the cation, and the negative ion, known as the anion, that's going to form an ionic compound. Since that electrostatic force is very strong, keep in mind it has to be electrically neutral, and since it's strong, it's going to be crystalline at room temperature, which means that these particles are not going to be able to move. So they are very rigid, like you would see in a salt crystal. You could crush that salt crystal, and we call that cleavage whenever we break it at these ionic bonds. But the fact that it holds itself together pretty well, it also has a high melting point before you can give these things enough energy to where they will actually start moving by one another and form the liquid state. And we name these, if you recall, by using the metallic name, in this case sodium, and we change the ending of the anion to IDE. Now, the simplest unit of this, instead of a molecule like you would have a molecule of water, the simplest unit of this would be the formula unit. Now, our most focus for this unit is molecular bonding. So that is ionic bonding. Molecular bonding is when the atoms share electrons. This is not sharing. The chlorine came in with its huge electronegativity, and the ionization energy of the sodium being low, plucked it, boom, attracted that electron from the sodium to the chlorine. Whenever you have molecular bonding, there's a sharing involved. So just to give you an idea, if we do hydrogen, hydrogen has 1 valence electron, it's in its 1s. Right? And we have oxygen. We have oxygen with the 2s and the 2p. Keep in mind I'm only doing the valence electrons here. So oxygen has 6. So here are the first 2. And then 1, 2, 3. So that's 2, 3, 4, 5, 6. Now what we will see is that oxygen has basically two unshared pairs in this 2p sublevel. Well, what will happen is oxygen will share this electron with one hydrogen and this electron with another hydrogen. And just to make this fit nicely, I'm going to go ahead and change this one to a downward spin, and this one to a downward spin. And basically what will happen is that these electrons will fit in kind of what we call a hybridized orbital. Hybridized just means it's changed a little bit. And that electron will pop into there. That electron will pop into there. And basically, I'm going to show you just kind of like a new structure for this. So basically, if we were to look at two hydrogens bonded to each other, and I'm going to just make that their 1s orbital. One hydrogen would bring in one electron and the other would bring in the other electron. And then we would have what we would call H2. Now this bond is represented by these two electrons. Now both of these are in an s orbital, and this is called a sigma bond. So sigma, and this is the symbol for sigma. It's like a cursive O. Same thing is going to happen with this hydrogen and oxygens. So basically what we get is there and there. And we know that we have to fulfill something called the octet rule. That's why chlorine wanted to gain enough electrons to get the 8, or why sodium, if it loses that one electron, it still has that 8 and the 2s and 2p. Well, oxygen currently right now has one electron from itself, that would be like the 2p electron, and another electron from itself, which would be the 2p electron. Now, this electron that makes up this side of the bond or whatnot would be, when I say side of the bond, I just mean it's in there. But that would be from the H, and this one of these electrons would also be from the H. So these are the electrons that are being shared. And oxygen also has its 2 electrons from the 2p and its 2 electrons from the 2s. So that means that it actually has fulfilled the octet, 2, 4, 6, 8. Each of these little lines, these are bonds, these represent a pair of electrons. This is called a lone pair of electrons. This is also called a lone pair of electrons. This is called a bonding pair or a shared pair of electrons. Now, with this, there's a lot of different interactions for covalent bonding, but it's not that repeating pattern. Now, hydrogen and oxygen in water, they can attract other water molecules, and we know that as surface tension. But at room temperature, water is a liquid. So again, they are electrically neutral by sharing electrons because nothing has gained or lost any electrons. They're just being shared. They consist of elements that are not metals, which can include the semimetals. And they can be any state of matter at room temperature. Water, H2O, well, that is liquid. You could have C12H22O11, that is solid. That's sucrose, right? You could have carbon dioxide, CO2, that is gas. We'll get into later why C12H22O11 forms a solid and CO2 forms a gas. But the idea here is that you can just have any state of matter at room temperature for molecular compounds. They typically have a low melting point. If you were to put sugar on to a pan, you could melt that pretty quickly, and that's a technique used to make caramel. Versus if you put salt on the pan, you're not going to be able to get that sodium chloride. You're not going to be able to get that temperature up high enough to melt that in your kitchen. Now these are named by the prefixes. There are 2 hydrogens, dihydrogen monoxide, carbon dioxide, because there are 2 oxygens. Keep in mind that the end of it always ends in IDE, and we don't say monocarbon dioxide, we just say carbon. If it's the first element and there's only one, we just say the name of the element. So the simplest unit of a molecular compound is called a molecule. One molecule of water, one molecule of carbon dioxide. So there's many ways to do this. The easiest way, again, is to check and make sure that you understand how to use the periodic table to find your valence electrons. But if we take a look, we could do the electron configuration. Say, 2 plus 3 is 5 for P. So the outermost shell of P contains 5 valence electrons. So P, 1, 2, 3, 4, 5. That's called the Lewis dot structure. It's one of the last things we learned last time. So it has 5 valence electrons. How many valence electrons does a molecule have if it's pH3? Well, we know that we have 5 from the P, so the P brings 5. How should I write this? Let's just do 5 valence electrons. And there are 3 H's plus H, each one bringing 1. So that's a total of 3 valence electrons. So the total here we have is 8 valence electrons to work with. What you're going to set up is a central atom. Now the central atom, we're going to start by saying it's the unique atom. It's the first one. Like whichever one there's one of, like H2O, it's the oxygen. That's the central one. pH3, the unique one, the one that there's only one of, is the P, so it goes in the center. Now if we take a look here, we have 3 singular electrons. We have 3 H's. So just like with the water, we're going to put these H's around the P and bring their electron with it. So we could rewrite that as pH3, and it does have that lone pair right there. Now obviously you could write this in any orientation you want to. Keep in mind these are 3-dimensional structures. When we write them on paper, that makes us think that these are flat, so that looks like a 90-degree angle. That's not true. But this is a representation we can use to write it out. So if we were to do NH3, this exercise does not need to go this far, but if we were to do NH3, nitrogen, we look on the periodic table, nitrogen has 5 valence electrons, hydrogen has 1 each, so that's a total of 5 plus 3 for 8. Sulfur has 6, oxygen has 6, so that's 6 plus 12 or 18. Quite easy. As we were saying, the octet rule basically makes molecules have 8 valence electrons. We're going to find out that this usually is important because sometimes it's a little bit different. That's for a different day. Hydrogen is definitely an exception. Hydrogen only has that 1s level, that 1s orbital, because s's only have 1 orbital. So it fulfills the octet by having 2. So atoms tend to fill out their outer shells. We know that we have S can hold 2, the PX, the PY, and the PZ each can hold 2. So that's 3 times 2, which is 6. So together these 4 orbitals can hold a total of 8. Since hydrogen only has the S, it holds a 2. I like to use straight lines. If you do use dots, you're recommended to use them like this instead of a dot and then another dot. I think the straight lines give you more area to work with. A pair of electrons, as I said, that's shared is referred to as a bond, and a pair that's by itself is known as a lone pair. So if we have H and F, HF, that's 1 plus 7 equals 8. We don't really have a unique one here, but there's no real center either. It's just HF. So there is 8 total. We can actually draw this like this and say, okay, well there's 2 taken up by that bond for 8. That leaves us with 6 others. Well, the hydrogen is not going to get any extras because it's satisfied with 2. Fluorine, however, needs 8. So 2, 4, 6, 8. Nicely done. Can you identify the lone pairs? They're all on fluorine. Can you identify the bonding pair? It's between hydrogen and fluorine. So let's try this. Ni3. 7. I'm sorry, not 7. 5. That's why we need our periodic table sometimes. Plus 3 times 7, which is 21. So that is a total of 26 electrons available. Out of these, which one is unique? That would be the nitrogen. So the nitrogen is going in the center. The iodines are going around it. Now there is a term, why did I put an H? Yeah. Don't see my, my stuff laying around, but that is kind of ugly. So I'm just going to scratch that out and start down here. So nitrogen, iodine. A term we like to use is symmetry. So notice that I have a symmetry here. If I cut a line right down the middle here, a sagittal line, if you took zoology, we have an eye on each side, and that's kind of a mirror of itself. That symmetry can help you a lot of the times. It's nice to have these molecules look symmetrical. So we have 26 total valence electrons. We've used 2, 4, 6 to combine these. So that leaves us with 20 valence electrons for lone pairs. Well, the nitrogen is not fulfilling the octet rule, so we know that it needs another set. Now, I like to use the lines. You could have put 2 dots there, but that represents a lone pair. It's perfectly fine. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So if we count those up, now I did recount in the 6 that I took, so if you only count the lone pairs, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Everything is fulfilling the octet rule. The nitrogen in the middle has the octet. Each of these also has the octet fulfilled. And notice again, this looks like a 90-degree angle, but we're going to find that those are not 90-degree angles because this is not flat like it is on the page. If you need more help for that, by all means, go down through here and take a look. You may want to pause this video now and then work through these on your own. 3, 2, 1, pause. And if you didn't pause, here's some spoilers. So we have 4 for the carbon. 4 times 7 is 28 for the chlorine. That's a total of 32 valence electrons possible. A skeletal structure is simply if we draw this without the valence electrons. So that would be the skeletal structure. The skeletal structure here, C was chosen to be in the middle because it's unique. 2, 4, 6, 8. 8 electrons from 32 gives me 24 to play with. Equals 24 to play with. So I'm going to redraw the skeletal structure here. If you are lazy, remember it's about your understanding and not filling out these note packets. So you can do that however you want. But here we have 2, 4, 6, 8. I need 24 more. Each of these on the outside is not fulfilling the octet rule, even though the carbon in the middle is. So that is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We said we had 24 left over after the 2, 4, 6, 8 were used. How many electrons did your Lewis structure have? 32 total. Draw the Lewis structure for ammonia, in the middle, H, H, H. 5 plus 3 equals 8. 2, 4, 6, 8. Hydrogen never has more than 2 of the electrons. And now you should work through page 13, I believe. You should be able to do this right here. So make sure you work through that. There are 4 problems there for you to do on your own. Thank you and have a great day.